In this video, we're going to be doing a Mathematical Reasoning FRQ for AP Physics 1. So in experiment 1, we have a student that released a disk mass m and radius r from rest at the top of a ramp that makes an angle theta with the horizontal. The disk rolls without slipping as shown in figure 1, and the rotational inertia of the disk is 1/2 mr squared. The frictional force exerted on the disk is equal to the force of friction. So on the diagram in figure 2, we want to draw and label the arrows that represent our forces. So you do not ever want to draw your components, for example, no Fx, no Fy on a force. You only want to have just the force that you have. Now, let's think. Well, because we have this ball that's on the incline, we have, acting at the center of mass, you have the weight equal to mg. You also have normal force at, very important, this is the point of contact, Fn. It is not like this. This is not normal force. It's not always going to be straight up. It's going to be perpendicular, specifically to the incline, because that is the floor here. It's not going to be like on the ground. You also are going to have the force of friction acting up the ramp. That is going to be opposing the direction of our motion, which is this way, right? Now, we can write these on here as well. So you're going to draw your weight force here, aka your force of gravity, and upwards you can draw your normal force, and then up the incline you have your force of friction. Now, the reason why friction is up the ramp, the disk is moving down the ramp and it's rotating currently in the clockwise direction, right? So that means the friction is going to provide a net torque that is going to cause the clockwise rotation. Now, because we know that, let's think about whether these forces are going to provide torque. So if we have our Fg, right, we know that Fg equals mg, right, and we know that it's going to act at the center. And you know that torque is dependent on, torque is equal to Fr sine theta. So if you have a radius, or not radius, well, it is the radius in this case, but if you have a lever arm, which is the distance between where we apply the force, right, and the pivot that we have. In this case, our pivot is the center of mass, because that's what our wheel is going to be rotating, revolving around, right, or just rotating around, and that r is equal to 0. So then you're going to have F times 0, right? So that's going to make the whole thing equal to 0. So you're going to have no net torque from mg because it passes through that center. Now, what about for our normal force? Our normal force is going to be along the radius through the contact direction. So that means that the torque is also equal to 0 because we're going to say r is equal to 0. Anytime anything passes through the center or your pivot, it means that you have no torque. So that means only our friction is going to produce our torque. Therefore, if we were to write the torque net on the block, that would be FFR. So that is your net torque on the block. Now, let's see here. We also want to, that is our net torque. So now we want to determine an expression for the net force that is exerted on the disk. So in order to do this, finding the net force, we always know that we have Newton's second law, which is going to be the summation of forces is equal to the mass times acceleration. And we are going to label this onto our graph, like onto our diagram, all the things that we need. So on our incline, parallel to the ramp, you are going to have this parallel component, which is going to be your summation of your forces that are in the parallel direction. And this is going to be equal to ma. So this is going to be the summation of forces. We know that down the ramp, when we're going down the ramp, that's the direction of our motion. So we're going to make that our positive direction. Therefore, when you break your situation, your inclined plane, into components, we have mg sine theta minus the force of friction is going to be equal to mass times acceleration. And we can also look at the perpendicular direction. So the forces that are perpendicular, we are going to have that's equal to ma. And this is going to be equal to 0 because we have n minus mg cosine theta is equal to 0. So the reason is because In the vertical direction, we are not going to have any net acceleration because it's moving in the horizontal direction. It's not going through the ramp. If it was going through the ramp, you would have a net acceleration. It would just like, fall through, but it's not. And that is how we can get that. Our two equations, F net here is going to be mg sine theta minus ff. And for our second Newton's law, we're going to get mg sine theta minus ff is equal to ma. Now let's go into our next question. See here, we have question 4. Derive the expression for the translational acceleration of the center of mass of the disk. Express your answer in terms of m initial, or m, theta, r, and physical constants as appropriate. Begin your derivation. Okay. Well, what we're going to have here is we need to look at both our translational and our rotational Newton's second law. Well, we're going to have in the translational direction the summation of our forces in the parallel, the forces that are parallel to our axis, our inclined plane, is going to be equal to ma. We saw that earlier. That's mg sine theta minus ff is equal to ma. You also have rotation about the center of mass, right? So when you have this, you're going to have the torque about the center of mass is equal to I center of mass alpha. We found that the total summation of our torque earlier was ff times r, because all those other forces, they didn't contribute to our torque. So we have I alpha, and because we have this disk, right, its I is equal to 1/2 mr squared. That's why we're gonna have this as our coefficient. They also give this in the problem, so you actually don't have to memorize I's, but I highly recommend that you kind of do, or you understand the concept of why inertia is larger and smaller. Inertia is resistance to rotational movement, and if you know that, it's going to help you on a lot of different FRQs, so I recommend that you do memorize them. So here, we can plug that in, and then you get 1/2 mr squared alpha, ff is equal to r. And then here, all you are going to do is, we know that we have our roll without slip condition. And what that states is that when we solve for a, when we have our tangential acceleration, we have our linear a is equal to alpha r. So then simply if we solve for alpha, that's just going to be a over r. Then you're just going to take that and just substitute it into the equation. So you're going to have ffr is equal to 1/2 mr squared a over r, and then this is going to be canceling out one of those r's. You're going to be left with 1 r left, and then this is ffr, and then this is 1/2 mra. This is ff is equal to 1/2 ma, because you can see that this r is canceling out on both sides. So now we have our first equation, which we're going to call 1, and, or actually we'll call this 2, and we're going to call our mg sine theta minus ff our equation 1. Now we're going to say here, we're going to sub 2 into 1. And if we do this, what we're going to get is our mg sine theta, right? And minus our 1/2 ma. This is going to equal to our ma. So then we are going to have mg sine of theta is equal to 3 over 2 ma. That's because you can rewrite ma as 2 over 2 ma, and then adding that 1/2 ma to both sides, you can easily see that you just add those numbers in the numerator, you get 3 over 2 ma. Now, we can see here, you can cancel out one of those m's, and after this, you get g sine of theta is equal to 3 over 2a. A is going to be equal to 2 over 3 g sine theta, and you have to remember fraction multiplication here, so you just are going to multiply by the reciprocal on both sides. So you can cancel out that 3 over 2, because that 3 and 3 and then 2 and 2. So that is your expression for the acceleration of the disk, actually. So we have to remember, like, let's look back at everything we've done so far. So we have that the component of gravity that's going to be down the ramp is going to translate the disk, and then through friction, that's how we're going to get the rotation. So then that translational acceleration is going to be less than g sine of theta. We had that coefficient is 2 over 3 g sine theta right here, right? Now, I can also label here the things that we broke down into components earlier. So you're going to have your, acting straight down, you have your mg cosine theta, because this is going to be your angle theta. And then in this direction, you're going to have your mg sine of theta. And your Fn is equal to mg cosine theta. Your Fg is going to be equal to mg sine of theta. And yeah. Now let's do part 2. So we have in experiment 1, the disk reaches the bottom of the ramp in time t disk. In experiment 2, the students release a block of ice from rest from the same height on a ramp inclined at the same angle theta, as shown in figure 3. Friction between the block and the ramp is negligible, and the block reaches the bottom of the ramp in time t block. Now we're going to indicate whether the time of the disk is greater than, less than, or equal to the time of the block by writing one of the following. So we have to remember that when we have a frictionless block, we're going to have the expression, of course we have our summation of forces parallel to the incline is equal to ma. So we have our mg sine theta, which is parallel, right? And then the m, and then the acceleration of specifically the block. And then acceleration of the block, if you isolate that, that's equal to g sine of theta. Again, you can see that m cancels out. And you have that earlier from part A, we found that when you have a rolling disk, right? You have A of the rolling disk, that's going to equal to 2 over 3 g sine of theta. So then we can compare. So we have g sine of theta here and 2 over 3 g sine of theta here. So obviously you can see g sine of theta is greater than 2 over 3 g sine of theta, because if you multiply it by a decimal, it's just going to shrink the value of the overall side. So then we can say that the A of the block is going to be greater than the acceleration of the disk. So we know that both objects they're gonna start from rest. They are both gonna move the same delta x down the ramp, same, we can just say distance actually, because displacement would be the shortest path. It is the shortest path, but we wanted to say distance here. And they also are gonna have constant acceleration. So that means that obviously the object with the greater acceleration is going to reach bottom in less time. Therefore, t of the disk is gonna be greater than the time of the block. So for our block here, our block of ice, it's not gonna rotate. So because the block doesn't rotate, the full component of gravity that acts along the ramp goes into speeding up the motion of the ramp. And we know that the disk, it has to translate plus rotate. So here UG, you have UG, and then here your kinetic energy is just K translational, right? And then here your kinetic energy will be equal to K translational plus K, or no, this is K translational plus K rotational. Sorry, I was not looking. This is the ball, and then this is the box. So this is K translational only for the box. So the disk, it has to translate and rotate. So that means some of that UG is going to go into rotational kinetic energy. So that means the center of mass of the disk is going to speed up less quickly than the block. Therefore, that means that the disk is going to take longer to reach the bottom.